Illya Klymov. We'll talk about TurboFan.
Yep.
So much fun, TurboFan. Thank you.
Okay, so it's nice to see you in that early developer morning, especially on Saturday. I'm also not so adequate right now, just from the train. So if I will be talking some weird things, probably this is TurboFan implementation, probably it's my bugs. Okay, whatever. Who am I? I own a small company, approximately 10 people now, at least yesterday. We are developing just in JavaScript, everywhere, Node.js, mobile applications, and so on and so on. Small clients like Microsoft, United Nations, and so on. And also I own a JavaScript courses called JavaScript.Ninja, where I'm teaching people to code in JavaScript. By the way, we are gathering new group for Node.js courses. And also I'm new meta level. I'm teaching people how they should teach other people JavaScript. Because I want our Ukrainian community to grow powerful, and this is impossible without cool mentors. I'm also a member of Kotans.org gang, and I'm pretty proud to being a part of it. But enough about me. Let's talk about the heroes of the JS world. I really think that V8 team is the heroes of JavaScript world because let's think, I'm in JavaScript approximately 10 years, I think. And the code I wrote 10 years ago was not so nice. Frankly speaking, yesterday, when I was preparing for other talk, I opened one of the websites I wrote 10 years ago. It was also a single-page application. And, well, I hope this site will never be found by anybody. And V8 team has to support this code. And V8 team aims to make such code run fast. They have all that ugly code, starting from jQuery version 0.8, starting from prototype framework, not to mess with common prototype in JavaScript. And they must, to make this code work, and they're trying to make it work faster. I have my classmate who is working as a part of V8 team, and sometimes he's sharing with me some different examples of ugly code which is met in the wild. Well, I was thinking that some things are impossible. They are not. And let's take a high-level overview of V8 architecture. Sorry, no laser pointer today. So, the V8 is a very complex system having a different level of JavaScript compiling. First of all, the first level is called ignition. And this is a level which was introduced not so long ago, approximately 1 year. And this is a tool which compiles JavaScript code in pretty hacky and dirty way, without possibility of further optimization. Oh, thank you. So let me try to swap. One. It's pretty nice someone is prepared. Oh. Awesome. When V8 team started to analyze the performance of real JavaScript application, soon they revealed some JavaScript code is executed only once. It's bootstrapping things, it's many other one-time code. Okay. It's a lot of code which is one-time. Okay. Initial setup. So whatever. And this code should be executed as soon as possible. Building the full internal representation of code is pretty long operation, and it is pretty useless for code which was run only once. And this is also a memory-heavy operation, because when we will see later, the full code generation generates a lot of additional information in memory, and this might be a problem, especially on devices which have low memory footprint, for example, Android phones. That's why a special framework called Ignition was built, which executes JavaScript, compiles it to the bytecode in pretty hacky and dirty way and unoptimizable. And this thing builds a reduced memory footprint and allows code to run faster. If the code runs more than once, or by using some weird heuristics, V8 is everything about heuristics. No one sometimes can tell why we are doing here with this magic number, why we are going here with other magic number. So the full code generation is performed, and we have unoptimized code. This is code which is usually executed on your laptops, on your desktop PCs, but when code becomes hot, it means it is executed often, optimizing compilers come into play. For a long time, there was the only optimizing compiler called Crankshaft, which produced optimized code, and it was pretty fast. But a year ago, actually 2 years ago already, a new project was started in internals of Google called TurboFan, because of course 2 optimizing compilers are better than 1. Now we will think about why. Instead of trying to improve Crankshaft, they built a new thing, and building at this line additional heuristics, which compiler will be called. Why we can't just expand Crankshaft to include all cool stuff we will see in TurboFan later? Actually, we have 2 engines. Crankshaft was built long ago, and it targets common code. When we call common code, we are speaking about all that bullshit we wrote years ago. jQuery stuff, a lot of early libraries, XJS code, no let, no const, no classes, all that stuff, ECMAScript free and lower probably. And it has a bunch of dark magic to make this code runs faster. As a side effect, it knows nothing about common JavaScript, and when it sees, oh, oops, we have a let here, I will not optimize this function at all, because I do not have any idea about block scoping. So Crankshaft targets to make old code fast. And it's just impossible to build a new optimization which will include both old features and new semantics of ECMAScript, let's call it still 6 and higher. That's why the TurboFan calls in play, and it's being invoked when V8 sees something which is called exotic code. Yes, compared to the size of existing code base, using of let, const, and all that fancy features are still called exotic for V8 team. And it is built with classes in mind, and even TypeScript developers were involved to make code produced by TypeScript run faster in TurboFan. So, if we compare Crankshaft and TurboFan in other words, Crankshaft is a normal Bruce, and TurboFan is Hulk. It is aggressively optimizing code, and when it fails loudly. 4 or 5 great fails of V8 optimization engine in previous year was reasons of TurboFan. TurboFan making wrong assumptions on code. Well, I was thinking that will never affect me. It will be just a part of funny tweets which roam here and there. But one day, it was December, I was solving a pretty simple task on some challenge, and I revealed a very weird thing. My function, which was pure, if it was executed 1,000 times, 3 times of that 1,000 produced the wrong result. It just differed. Okay, I said, you say we can trust Node.js in banking applications? Okay, definitely not the thing I want to meet. And just by adding the eval, the magic word which disables any optimization in every function, the error was gone. The TurboFan is still considered in early beta. You know, it's called better than nothing. And that's why it's not enabled by default for all code in JavaScript. Instead, the Chrome has a built-in heuristics, and Node also has a bit altered one, when to enable TurboFan to assume it's safe. TurboFan is huge. It's just a bunch of totally sometimes unrelated code, and we can speak about TurboFan for hours. When I was speaking about TurboFan with V8 developer, our talk was about 5 to 6 hours. When he was saying, "Oh, look, this funny hack, and this hack makes this code twice faster, but has a negative effect on this one." So that's why, since we are limited on time, I've extracted 3 features which you should be aware. Probably you know about the rule of leaky abstractions by Joel Spolsky. And I extracted these 3 features because they produce us a better understanding how to write better code. So, 3 main features from my point of view of TurboFan is the sea of nodes, the maths, and inlining. I know that inlining seems pretty obvious. It's simple, yes? Take the code of the function, put it inside the other function, you've inlined it. But as always, the devil is in details. So, the sea of nodes. How do you understand your code? How you make assumptions about your code? Let's see the simple loop. Pretty trivial. We are just looping over the code, and we are just making sum of elements in array. If we look how this code is compiled into bytecode, it's something JavaScript-like, so you will not be scared with machine codes. We can see pretty things. Each time, we need on each step of the loop load array length. Of course, it could be changed during the loop. We need to check if our index is inside of array bounds. This is required because accessing the index out of bounds and accessing the array index in bounds have different semantics inside V8 engine. So we need to check it on each step. After that, we are loading the data from array. As you probably know, that arrays in JavaScript are not necessarily stored in the ways, for example, the arrays are stored in C. I mean, it could be more than one part of memory. It is actually the list of lists, and so on and so on, and so on. But of course, this code is bad. Why? In a perfect world, we should be able to figure that since we are just iterating the array, there are 2 main assumptions about this code. First, length is never changed. Pretty obvious. And second, we do not need to check that our index will be out of bounds because we are iterating over the array indexes. So in general, we would need to eliminate this check and this check. But what's the problem here? Why it is not so simple to do that for compiler? It's a common syntax tree representation of this code. This is the tree, so the 4 statement is compiled into 4 branches: initialization, test, update, and body, and so on. This tree is single linked. That means we are traversing tree from parent to children's when we are generating bytecode. And moving back is pretty expensive. If we convert this tree to the double linked list when each child has links to parent, we will have multiple issues with traversing because it will be now infinite. It will be not a tree in the strict way. You understand, yeah? Linked list. And in other way, in order to make some additional knowledge about the code, we need to go bottom, check, for example, body that we are not modifying lengths. And after that, go back and generate the proper code for 4 statement here. So we are generally going down and up, and this is very bad in terms of quickly generating code. That's why sea of nodes come to it. If you're really interested with it, and you are, for example, at least familiar with Dragon Book about building effective compilers, there is a perfect post by Fedor in Dultni. I can't speak. Yes, thank you. One of the V8 developers. He has an awesome blog post about it. But the main idea of C of nodes that it is another way of representation the code. It's not the tree here, but it's basically a graph where we have links, and links are of two different types. One type is a common code flow, and another type of code flow is side effects, something that changes. We all love functional programming. We all know that we have effects. And using such representation, which is built internally by TurboFan, we can make assumptions about the code just by checking how many side effects are affecting one or other node. This is a pretty effective thing which allows us to make proper assumptions, and TurboFan in fact do some funny things which are closely connected to functional programming. Each assignment to the variable is treated like creating new variable. It's pretty obvious. In order to track changes, we need to know each time we change variable, it's actually a new value. Functional programming, no variables, cool. Each side effect is also treated as control edge. Each time you emit a side effect like changing global variable, manipulating DOM and so on, it's another point when we can't guarantee that your program is safe. And if your code is pure, it really makes wonders. What I mean? Well, if your code is pure, sometimes it is safe to reorder the execution of certain code lines. If your code is pure and we know that, okay, this line and this line is not connected. And V8 knows, okay, I just retrieved from the memory this variable. Probably I can do some more operations on it before I put it back somewhere or throw it away. In real world, TurboFan reorders execution of your JavaScript statements in the way it could be performed more efficiently. And the magic here is if it makes correct, sometimes it fails, it makes your code to really run faster without you even thinking of it. That, okay, if I manipulate this variable here and here, it will be somewhere in CPU cache or somewhere else, and it will be faster. No, it does it for you. So in general, by having this graph and by having pure functions, we have an ability to effectively reorder code to perform it faster. Free optimization for everywhere. That's why the V8 developers are really speaking a lot about functional programming, and they're really spreading the world how functional programming is awesome. Another thing which you should probably know about TurboFan is very fast mathematical operations. Why it is related? Well, it seems that ASM.js will never go live. I mean the proper ASM.js support in V8. But still, there are a lot of situations where we're just doing maths. Cryptography, some operations on images and so on, it's just pure maths. And maths should be fast. And making maths fast in dynamic languages is very problematic because, okay, you have this type, and what is it? Is it an integer? Is it a long integer? Is it a double? Who knows? And the fast math is one of the key features of TurboFan, which allows ASM.js-like code, not necessarily ASM.js, to run very fast. There will be some assembler listings. Get prepared. So, first of all, the TurboFan introduced a new way of storing numbers. Integers are treated treated in memory like first 32 bits are the real value, and here zeros. Here until the end of the presentation, I will be speaking only about 64 bits architecture. TurboFan is absolutely not effective of 32 bits architecture, and well, who cares right now? We have integers which are represented a pretty ugly and hacky way. Since in JavaScript everything should be a pointer to the real value. It's the way the V8 works internally, and they represent this integer as magic pointers, which has the last 32 bits aligned as zeros, and integer is encoded as pointer, which is not a real pointer. It does not point to real memory. That means we can save one step. We have the pointer, and from that pointer we can figure the value. Dark magic? Yes. Should you do this in your C code? No, never. But it really saves the day when we are doing some math. And other numbers are stored on heap in common way. We have a pointer, and somewhere in heap the real data is stored. And we have several small, fast cases. When we make operations on small integers, it's a pretty obvious thing. We are doing a lot of operations on small integers. When we're operating on numbers, on heap numbers, when we have oddballs, I think that word can't be properly translated in Russian. So when you're doing some weird maths on undefined, null, true, and false, you know, everyone loves to sum undefined plus null and to divide it by false. When we are doing math operation, you know, the only one plus on strings, these 4 cases, I mean that, for example, 2 arguments are strings or 2 arguments are small integers, are using the handwritten assembler implementation. So the V8 team took the real world assembler guy, they're still alive, you know, and written a very optimized code for these cases. It is extremely platform dependent. It is extremely dependent on V8 internal realization, but it is pretty fast. Other objects are just using a generic C++ implementation, and it is really slow. The difference could be up to 10 times. But another important thing, which is introduced by TurboFan for maths, is type feedback. In previous, the type feedback was working only for objects. But what does it mean? It means we have a simple function which just introduces a new variable, which is the sum of A, and returns another variable. When we compile this function into some kind of bytecode, we have a so-called feedback vector, which is initially uninitialized. Which it means? That means that V8 has no idea of type C and has no idea of type of return value. After that, someone calls your code. I promised you. From C, okay, this is integer. Actually, it is small integer. This is also integer. So the feedback vector is gathered. Okay, this is the operation of integer, and the result value will be integer. And the second value operation is actually the same. This is compiled to pretty simple assembler code, really simple. Who can? It is colored. So what we actually do, if you are maybe too tired to learn this assembler in the early morning, we are checking that input has a proper type. We are making a real operation of sum. We are checking for overflow. GO, if you are not familiar with modern x86 assembler, is jump if the overflow bit was set. We are checking another input. We are doing sum. We're checking overflow. We are returning the result. So basically, check, operation, overflow, return. While this is doing good, nothing will be changed in this code in the memory. V8 is like a very junior developer. It really hopes everything will be fine. So the whole idea of optimizing the code is that people are calling it in normal way. That if you have a function and you're using it to sum numbers, you will not use it to sum strings. But shit happens. And one day, we are doing a very small change. Now we are doing an operation not on integer numbers. We are doing on double type, or in general number. What happens?
this check fails, oh no, this check will pass, sorry. Because what we are doing in this check, we are checking the type of A, it is still the integer, but this check will fail. It will see that return type of the B and the type of B is not no more the integer. We are doing a wrong assumption. Here comes the de-optimizer. De-optimization is very expensive operation. What it does, it sees, it take a look where your function is currently at execution time, looks backward for a last side effect which was performed by your function. At this situation, it will be the start of our function, but in general, it will be the last side effect. And after that, fails back to executing it once again in de-optimized mode. Very slow operation, but what happens after that? The feedback vector is now updated with a new assumption. It seems okay, it's definitely maybe not an integer. Let's assume it will be always a number. So we are updating, building an optimized frame, and generating new assembler code, which is of course even more easier than previous one. And the general idea is that now it's just doing the same thing which was done before, but now it's taking into account double numbers. If for some reason you will do that operation on strings, for example, there is a very high probability this code will be thrown away. The optimizer will say, oh my God, this function is called with so many different types. I will never optimize it again. At the moment, V8 has a limit for 32 attempts to optimize each function. If you are playing with your function here and there, and V8 makes wrong assumptions, after 32 calls, the function will be marked it is okay, I will never optimize it again. It usually helps, but it usually greatly reduces performance of your code. So if you're a good developer and want to keep your code fast, please try to use one type to try to use the same types when you're using the code. I mean that, okay, if in JavaScript we will have strict type check, try to follow it. You know, TypeScript or who said flow type, whatever. It's really important for performance. And inline function calls, it's, like I said, it looks pretty obvious, but there are a couple of major changes which are greatly affecting the performance of modern code, classes especially, and the transpilot code. First of all, let's see how internally the call of JavaScript function is represented. We have the target, it's the code which needs to be executed, receivers who will consume the result of our function, effect, which means all side effects which will be performed with side functions, and the control, which is internal engine of V8, which allows to control function behavior. For example, is if function we are calling is actually generator. So we need stop, resume, and so on. This is a control. And let's assume we have a pretty typical code. When we have the function which is, we are checking some variable, and after that deciding which function will be called. So, for example, if our door is open, we will call, is closed, we will call open. If our door is open, we will call close. And after that, we will execute this function. The crankshaft optimizer will never touch such function because it has no idea, basically, which function will be called here. TurboFan analyzes your code flow. It says, okay, it's just two options. And when the scope of possible functions is pretty small is currently limited to 8. Like I said, a lot of magic numbers inside. So it is say, okay, I will replace this pretty obvious call with such big strategy, the main idea here that we are reusing a lot of internal nodes like receiver, control, and target. We are effectively reusing them. So in general, we have approximately twice less memory footprint. And in general, this thing is optimizable because this is the code understands. It's like you wrote a normal if, and it's a normal analysis. So basically this code, you can think it's in your memory, is compiled into if and could be optimized. Pretty common pattern. That's why it is. It was a very important for TurboFan to optimize it. And another very important thing is context-dependent inlining. Let's see. It was a request originally by TypeScript team, but for example, Babel does pretty much the same. This is how the code is transpiled when you are using class child extends base. In fact, this is essentially the same representation of what V8 does internally. That's why it works both cases. So what's the problem here? We have some base class definition. We have child, which actually immediately invoked function expression to effectively isolate code here, which extends child from our superclass. Super is passed as base. And after that, we are calling constructor. The problematic point is here. What's the problematic point? Function calls is actually pretty cost you pretty much. In any language, in assembler and so on and so on. And in perfect world, you should inline the code of base constructor here. So you can't go here and there and so on, because the only thing, the super, the only option, it will be equal to base. It is the only option of calling this code. It's immediately invoked function expression. Since Crankshaft was not unable to figure that, it was never looking to the closure variables, this code was never optimized. But for now, this is the one thing which was TurboFan was originally started for. Compiler can understand the context of each closure, and if code inside is hot, that means invoked pretty often, the code inside gets inlined like, okay, I see this variable is equal to this one. And if by some weird magic, not in this code, the closure will be called with other variable as argument, and new optimization context will be called. Like I said, we have a tons of magic numbers here. For example, in version 41, if I'm not mistaken, in Chrome, the optimization, the inline limit of functions, that means how many statements your function may have before it will be inlined, was raised from 196 to 200. Really important change, but this change, just by increasing this number by 4, gave the Chrome approximately plus 5% in some score. I don't remember. It was Octane benchmark. That's why I think they have a special person in V8 team who is tuning these magic numbers, and okay, let's look what happens. Because no one, I really tell you, no one can explain why this number should be here. And a lot of dark magic in Crankshaft, especially, which is dealing with old code, is about, okay, this limit seems reasonable, and let's speak honestly, with this limit we have high score in benchmark. Everyone is measuring the performance on common benchmarks. It's actually very bad, but it's marketing. So basically this is 3 features I wanted you to know. If you know these features, it's really inspiring you to write a better code. There is probably one more small thing I want to tell you, and this is about maths. There is one more thing you should know, and which is really implemented in TurboFan and is related to AsmJS. You know how you know that this code is in AsmJS. You have the code, and after that it is pipe 0. Yes? Something that telling us that this is integer maths. So it could be made faster. This is in V8 decided not to implement the whole ASM.js infrastructure. Instead of that, they implemented the thing called type truncation. And type truncation is viral. What does it mean? It means that if it sees that in some reason you somehow converted the a to the integer, no matter which type it was original. For example, it was a float, you made pipe 0. It will understand that all future operations here will be with integer. And can optimize it and check for overflows and so on and so on. Previously, there was no way how you can reduce the type. You can make the type wider. That means that you are starting this integer like in this example, and after that widening type to number. But there was no way to make type more strict inside compiler brains. But this was one pretty important implementation because, okay, you receive function arguments, you convert it guaranteed to integer, and now it could be performed on mathematical processor unit, and it could be made faster, and optimizations are made on assumptions that this is a fast integer. So, like I said, this is deep internals, and real performance gain from these things are actually from 20 to 30% on real code and approximately 100% on specially crafted code to demonstrate that TurboFan rules. You know, benchmarks. But the main idea is, and in fact the main idea is called, that the way the compiler inside V8 develops, it really encourages you to use functional programming. As soon as you use functional programming, the compiler is happy. It can make more safer assumptions. It can reorder your code to be executed more effectively. And one day, it's not here yet, but it is slowly coming there. The code written in functional way will be faster than code written in imperative way. It's not on the table at the moment, but is the really long-term aim of the V8 team. Okay, and this is all, I think. Any questions?
Way over there.
So, really basic question.
Yep.
Okay, no problem.
I speak Russian too, honestly.
Not bad.
So-so.
Okay, so when TurboFan do optimization, it would save previous version, or it always would be like new one?
It is always a new version.
So when you call it like for integer again and again, it would never use like number, yeah? In your example.
Yes, it is for each function there is only one instance of optimized version stored in memory. That's why each time it is using it in other way, the old version is thrown away. And it really sucks, but it was done because a long time ago they were experimenting with multiple optimized versions and revealed that it is bloating the memory. And you know, Chrome is pretty likes memory already. And that was a real issue, how to track the life of these optimized functions. So they said, okay, one optimized version will be enough for everybody.
Illya, could you give, for example, a couple of advices to avoid the optimizations in real-life code? What would you advise to someone?
I'm talking about performance optimization for several years in a row. By the way, if you're interested in this theme and want some basic introduction into how V8 works, you can take a look into my talks in Minsk previous 2 years. It's called FDConf. I was speaking 2 years in a row about performance optimizations. And in general, first one, keep your functions First, like I said, keep your function consistent in terms of types they receive. The second thing, which is extremely simple, which everybody probably knows here, but every time I'm optimizing the code, I see this issue. If you're using some kind of classes, everything invoked with new, never add new properties anywhere except constructor. Every time you're adding new property to an object which has some class or hidden class, it means it probably even if you're not using classes, but you have some multiple objects which share some structure, Chrome will optimize it and create so-called hidden class. Every time you add property, Chrome tells you OMG and will create a new hidden class, and this is a great performance decrease. So these two things could really help with the code, and this is pretty obvious things which is pretty easy to miss. Okay, I will just store this variable in this object, no one will notice. It's a common situation. I was optimizing the code of some game engine. This is really true. What thing I also revealed, strict typing things like TypeScript. I really don't like TypeScript, sorry. And flow type helps. Flow type is extremely nasty, extremely strong about making assumptions about types. It will beat your hands every type. You are thinking, okay, I'm pretty sure here it will be here the one type. Flow say, prove me. If that could not be mathematically revealed from the code, Flow will say, I don't trust you. And this is a good thing in optimization.
No more questions. You're a lucky person.
Yep.
Another performance advice, keep your functions small. Smaller functions are easier to understand, thus easier to optimize.
And smaller functions could be inlined.
Yeah, it doesn't matter. Just keep your functions small, keep your files small, keep your projects small.
Keep your company small.
Keep your company small, keep your team small, keep everything small. Keep your salary large, yeah. All right, thank you, Illya. It was a pleasure to listen, and the assembly slides were amazing. Thank you.
Okay.